Okay, so before we go into our last part on multivariable calculus, we just need to cover a few more things on the derivative, and notably what we can use it for in terms of finding minima, maxima, and things called points of inflection. So in the same way that if we had a function f of x, and we take its derivative, we can write it df dx. We can also take the derivative of that function, because the derivative of a function is oftentimes a function with itself. So if we were to take the derivative of this as well, so if we were to take d dx times df dx, we will write this as d squared f dx squared, and so on and so forth. So we can take any number of derivatives in this way. So if we had d dx, so d dx of blah, 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 of df dx, we'll say like n times. We can write this as dn of f and just dx to the n. And this can be quite useful for dealing with trying to find either local or global maxima or minima of graphs. So if we had, say, a graph here, we'll say like this. We'll call this f of x here. So we can, by looking at it, we can see that there's a maximum over here and there's a minimum over here. But how can we tell this from a graph or a calculus point of view? How can we find where these are without just drawing out a graph and hoping for the best? So this is what we use our second derivatives for. So when you'll imagine if we're at a minimum or a maximum, right? If we draw out all of the tangents to this curve, all of our tangent lines, at a maximum or a minimum, these will be completely flat, right? Oh, completely flat. So if our derivative is 0, no matter where we are, or sorry, our derivative is at 0 at a certain place, that means we're either at a maximum or a minimum. So if we were to find, say, we had to say a function f of x is equal to x squared plus 1, right? We have then df of x, or df dx rather, is equal to 2x. And if we let that equal to 0, we find that this happens at x equals 0. So we know that we have a maximum or a minimum at x equals 0. Now, if you look at the graph, you'll see that that's a minimum point. But if you were to say make this into a minus x squared, then you have the derivative being a minus 2x, but x would still be equal to 0. But in this case, it will be a positive, or it would be a maximum. So this doesn't really tell us too much information besides the fact that it's called a stationary point, or it's a maximum or minimum or anything like that. So that's what we need our second derivative test for. So if we take our second derivative of a function, and if that is greater than 0, then we'll know that our point is a minimum. If our second derivative is less than 0, we'll know that this point is at a maximum. And if our second derivative is equal to 0, it's called a point of inflection. Sorry. So this is, when you're dealing with calculus, especially in your beginnings, you can basically just learn this off. And then if you're ever asked for finding the minimum of a certain function, all you need to do is go into your second, first derivative, find, so actually, I'll write it out. So if you have a question, say, find when some function f is at a minimum. So I've just shorthanded minimum. So we take the derivative of f with respect to x, or if indeed this is an f of x, rather. We set this equal to 0, and then we solve for x. So this should give you a number of x values depending on what function you're originally given. Then we take the second derivative, and we test out all of these x's that we've solved for, and for x, and then we find an x such that the second derivative is greater than 0, and that gives us a minimum point. Now, if that point is a local minimum, which means it's only, say, in this case, if this function then went off to go down to the bottom a while away, this point will be a local minimum. So it's the minimum of the surrounding function, but not over the entire function itself. And this is the same with a maximum. If it's, say, a maximum here, but not everywhere, it's called a local maximum. So this is kind of an important idea we need to understand moving into partial derivatives. Okay, so when we're dealing with partial derivatives, it might sound a little bit weird, and a lot of times you're kind of slapped with it out of nowhere at the beginning of college. And it really is not too big an issue. It's nothing that you can't do with knowing this. So we'll describe it right. So if we have, say, some function v that is a function of x, y, and z. It could be 2x plus 3y minus 11z. It doesn't really matter. But we'll assume that it's smooth and continuous at every point, just to make our own lives a little bit easier. Now, we can take what's called the partial derivative of this function, which is denoted like this. We'll say we'll take it with respect to x. We can denote it like this, or we can denote it like this. The second one is generally my favorite. I think it's just faster to do. But either or will work. So what this means is we're going to vary x and keep everything else stationary. Y and z will treat as constants. They might as well be constant. We don't care about them. We only care about what x is. So if we have, for instance, some v equal to 2x plus 7y minus 12z, and we want to take the partial derivative with respect to partial derivative of v with respect to x, we know that this has an x in it, so this function, this part of the function will vary, but these two we can hold constant, so we only get a 2. Or if we have, say, a u function equal to, let's say, 14xy minus cos of z. If we again want to take the partial derivative with respect to x, we know that this function here, this part of the function, has no reliance on x whatsoever, and so it goes to 0. We don't care about that. We'll know that when we have a single x by itself, that will go, like we had here, that went. But now that we might not be sure what to do with this y, but remember that we're keeping y constant. It's just as constant as the 14. It's practically the same thing as far as we're concerned. So we'll get 14y as our answer. So this idea is, it's fine once you get your head around it. It can just be a little bit daunting the first time you see it. Okay, so now that we understand how to find minima, maxima, and general stationary points of a function, we can now move on to finding the partial, or dealing with multivariable functions and finding stationary points of them. So when we have a function of more than one variable, they usually create a surface. So if we had a function, let's say that gives an altitude a, that's a function of x and y. So it's like a terrain or something like you'd find in mountains or whatever, and it gives you different altitude depending on where you are. Where we would be trying to find points of inflection, or sorry, not stationary points, we need to find not only when one derivative is equal to 0, but all derivatives are equal to 0. So when we have all first derivatives are equal to 0, rather. So if we can take the partial derivative with respect to a with respect to x, this must be 0, and the partial derivative with respect to y of a must also be equal to 0. So this is like if you imagine a mountainous terrain or a terrain in general, and you had a valley in that terrain, you might be able to find that it is the minimum with respect to one variable, but not with another one. So really, to find a minimum or maximum or anything like that, you need to make sure that both of your derivatives are equal to 0. So we can generalize this to functions of more than 2 and basically say that the partial derivative with respect to any x sub I of the function v must be equal to 0 for all, which is what this symbol means, x sub I. Okay, so now that we have that generalized, we need to see how we can make this figure out if it's a minimum, maximum, or what's called a saddle point, which is the multivariable equivalent of a point of inflection. So we're going to need to define some more second derivatives. Obviously, we can take the derivative of a function with respect to the same variable twice. So say we could have d squared x a, if we're going back to this example here. So we can say this is a second derivative, right? We'll express this in the fractional form, d squared a partial x squared. We can also say this here. So the second derivative of a with respect to y. So d squared a dx squared, sorry, dy. And then we get into a little bit more, this is where the fact that this multivariable really comes into play. So we could take the derivative with respect to x of a, and then another derivative with respect to x. Why can't we take the derivative with respect to x and then the derivative with respect to y, for instance? So we'd end up getting d squared a, say dx, or partial x, partial y. Anyway, so we could do this just as well. We could do those, or we could say take the derivative of a, so we have partial y, partial x. Now the question is, does it make a difference? Does us taking the derivative with respect to y and then x matter or if we took x then y, or any combination of multivariable variables, or of variables in a multivariable function rather? And that depends on the function itself. So if a is continuous itself and its derivatives are continuous, I think, we can basically say that these are equal. So with all well-behaved functions, we can say that these are equal, and they don't really make a difference. So the kind of last part we need to know in taking up these stationary points is a little bit of linear algebra, which we wouldn't really come across too much in school. So with this information here that we have, actually, here, we're going to define what's called a matrix. So you can think of a matrix, it's called the Hessian matrix, but we can think of a matrix as just a way of storing information from now. They multiply vectors in ways, they multiply other matrices, but we don't really need to know that too much. We can define this as dealing with other other second derivatives. So we can have this as d squared x, or we'll keep in fractional form. Dx squared, d squared a, dx dy, and d squared a, dy dx. D squared a, dy squared. So this is what's called our Hessian matrix. Okay, so now that we have our Hessian matrix defined, we can do some operations with it. Now, these operations don't really need to mean anything to you. They shouldn't mean anything to you in fact, but they will eventually, and they are quite important. So the first one we'll have is the determinant of a matrix, of the Hessian matrix in particular. Now this is quite important, but we don't really need to understand what it really means now. But we can say that this is d squared a dx squared times d squared a dy squared minus d squared a dx dy times d squared a dy dx. Right, so this is our determinant. This is quite important. And then we also have what's called the trace. The trace of the Hessian matrix is equal to d squared a dx squared plus d squared a dy squared. Okay, so now that we have our determinant and our trace defined, we need to come across here, and this is where we figure out if what we're dealing with is going to be a saddle point or a minimum or a maximum. Right, so if we have, if we have our determinant of h is greater than 0, then we have, and then if the trace is also greater than 0, then we have that it's a minimum. If the determinant is positive and the trace is negative, we have a maximum. And if the determinant of h is negative, regardless of the determinant of the Hessian matrix is negative, regardless of the trace, we'll have that this is a saddle point. Okay, and that's really all you need to know about finding a multivariable function is at a minimum, a maximum, or a saddle point. And that really encapsulates everything we need to know about multivariable calculus for the time being. There's a lot more, and it's very interesting, but for now we are finished with our mathematical prerequisites and ready to head into some physics.